Welcome everybody to our presentation on interpreting radar, guided wave radar echo curves. Thanks for joining us this morning. I'm Karl White. I'm the sales representative for Northwestern Colorado and Northeastern Utah for Rosemount Measurement Products. With us today, we have John Butler, who is the regional level business development manager, and Wayne Buhler, who is the regional sales manager for Colorado, Utah, Wyoming. I have John and Wayne have many years of field experience with guided wave radar and looking at, reading, and interpreting plots. I rely heavily on them when I'm helping you troubleshoot what's going on with your radars, probably even more so than anybody at the factory, because their experience is real hands-on out in the field. John spent quite a few years as field service technician, and Wayne has always had his hands on the stuff that he's working with. So with that said, again, I'd like to welcome everybody here. This is being recorded. If there's any of you that would like to have the recording, I can send that out later this week, and I can also provide that to anyone that wasn't able to make it this morning. We have everyone muted right now. While we're going through the presentation, while we certainly welcome questions and everything, we're going to have you use the chat function until we come to the end of the presentation, and then we will turn everyone's mics on and we can have a live Q&A session there. All right. Turn this over to John and Wayne.
Okay, Karl, thank you. So this is John Butler. Thanks everybody for joining this morning. Really appreciate your time. We're going to talk about the Rosemount 5300 in particular. This is our probably the most widely used guided wave radar that we have. So this is the one that would apply the most to most of the applications that we're going to discuss. Kind of our agenda. Start out before we can really talk about a radar echo curve and how to diagnose or even read an echo curve. We'll talk about how a guided wave radar works. So with the radar, it sends a microwave pulse, travels through, in this case, we'll say vapor or air. Has a very low dielectric, we'll say 1 for air or vapor. Then once it reaches a different media with a different dielectric constant, it gets an impedance change. Part of that energy that is transmitted from the microwave is then returned back. The time that it takes to transmit and the time that it takes to receive it back, we correlate that into a level measurement. Part of that energy, after you get the first signal back, part of that energy keeps traveling, reflects off the second surface. In this case, we'll say this is oil, the lower product being water. Oil has a very low dielectric, around 2 to 2.5, where water is really strong, like 80. So you get a smaller reflection off the oil, you get a really large, strong reflection off the water. That's why when we say, in order to measure level and interface, we always have to have the higher dielectric product on the bottom and the lower on the top. And you'll see why on this video. This kind of shows you what we're talking about. So once that microwave signal is transmitted from the electronics, it travels down onto a probe or a cable. That's where it gets the guided wave name from. with that guided wave, you get a large reference pulse, right, where it comes onto the probe. That's our reference reflector, or reference pulse. It uses that reference pulse to tell the distance that it's traveling. So it measures from the reference pulse down to the first surface, which in this case would be hydrocarbon or oil, and then you get the second surface. So it uses that. So that reference pulse is very important, and we'll talk about that here in a minute, why that is so. When you're looking at an echo curve, get used to looking at the reference pulse. And when we say the signal strength, we measure that in millivolts. So if you look at this, well, this is not a good plot, but the signal strength of the reference pulse can tell you the health of the device. In this case, you get a strong reference pulse where it travels onto the probe, goes through the air, hits the first level pulse. You get a signal strength off of that, which is pretty low. That would be hydrocarbons, and then it travels on. To show you what it kind of looks like. So if you're thinking of this, this will be the tank, top of the tank. This will be your liquid surface, and this is what the plot looks like. So the plot is read actually from left to right, where the tank is top to bottom. But this is what you're actually seeing on the plot itself. We start from the 0 axis here, which is where the reference pulse should be, measure down to the surface. We get a reflection. And depending on, like I say, the dielectric strength, the signal strength will be stronger. So hydrocarbons, you can basically say 2,500 millivolts or less, where water is going to be really strong, 6,000 to 8,000 millivolts. And if you look to the left of the echo curve, you'll see a chart. This is the millivolt scale. It starts at 0. It goes negative and then positive. So the positive is really all we're reading for the peaks. The negative, really the only thing that applies for the negative scale is the reference pulse itself. So this green dotted line or green line you see here, that's measuring the reference pulse. That's all it's doing, and it's set automatically. So that's not anything you need to mess with. So looking at the plot, again, you have the reference pulse. You get a reflection off the surface. And depending on the dielectric, if it's hydrocarbons, you would see a probe impulse also. If it's water, you won't see a probe impulse because the amplitude of the surface is so strong. If you talk level
John,
and interface,
you want to back up one?
Yeah.
So just one other thing to point out is that scale on the bottom, it's on the x-axis, is in distance down the probe. So you're starting at 0 where the red line is. And then as you go down the probe, that's getting farther and farther away from the head. So that's distance, not level. So kind of backwards of level.
Yeah, that's a good point, Wayne. I forgot to mention that. So yeah, so another thing, if you're looking at the plot, so your 0 is where you start from. Travel down. You have a red line here that indicates the probe end, whatever the length of probe may be. And then you have the dotted brown line, which is the tank bottom. So that we call that the tank height or reference height. When you configure the radar, you have to put in that reference height. You have to tell the radar how tall the tank is or how tall the chamber is, and then the probe length. So it kind of shows, in this plot, it shows the measuring range. Normally it's going to be from red line to red line, but that's not always the case. It's actually from 0 to tank bottom on some of them. It depends on which type of probe you have. Interface, same thing. Your reference pulse, your first reflection off the surface, which would be the oil. Second reflection, water. Second reflection is always going to be a lot stronger. The signal strength is going to be much stronger because of the dielectric of the water. And when you see this little arrow that brings it back over and puts a dotted line, the dotted line is where that interface is actually at. The reason being is as the radar signal travels through the oil, which is the low dielectric, it slows the speed of travel down so that this interface peak actually appears further down than it really is. The radar uses a couple parameters and recalculates it back. So the dotted line is where the interface actually is. And again, you can see this would be an indication of water, real strong reflection. You wouldn't get that probe and pulse.
So just maybe one other thing to point out here is, what's the area we're really looking at for peaks, right? It's really above the blue line and between the two red lines. That's really the area we're looking at for surface reflections. So a lot of people look at, beyond the red lines, we don't care on either side. That doesn't really affect things. It's really between the two red lines and above the blue line, and the blue line's a threshold that you can set. The pink line is also a threshold you can set, but we're looking strictly at any peaks that go above that blue line.
Yeah, that's a good point, Wayne. So the way the radar works, the first peak that breaks the blue line is considered the level. The first peak that breaks the blue line and the pink line is the interface. This is just another example of what a plot would look like. Again, there's the threshold. The blue line in this case, we're just measuring level in this example. The measurement range is from 0 to the tank bottom. In this case, you're getting a probe in pulse because it's a lower dielectric, right? So you still get a probe in pulse. This one's positive, indicating something's touching. So if you have a positive probe in pulse, it's usually because there's something metallic that is touching. Or in some cases, you may have a weight, and you'll get the pulse off of the top of the weight, especially on an empty tank. But it's always a transition change is why you get that. If there was no transition, then you get a negative pulse, which is typically what you'll see. So one thing on the red line, that's why you can't always just say red line to red line, because that red line indicates what we call the upper null zone or hold off distance. Normally we'll set that if there's a nozzle, kind of like the picture shows here. Let's say there's a 10-inch nozzle. We're not going to measure up inside the nozzle, so we'll blank that part out, that 10 inches, the nozzle height. Normally, if it's a direct mount, like it just screws into a bushing, we're not so concerned about that. Well, there's not much really reason to put an upper null zone. One of the things you have to really be careful of when you do this is you don't want to put your upper range value or 100% above this upper null zone, because the radar will stop reading once it hits that mark. So we'll talk just a second about probe types. The most common for these applications is going to be this flexible single probe, stainless steel, has a weight on the bottom. There's several different types of weights you can put on there. You can also do Teflon coated. If it's a chamber application, it's usually going to be this rigid probe with a centering disc on the bottom. But for the most part, for upstream oil and gas, it's always a single flexible. And going back to that reference pulse, why that's important is you can see different probe types give you different reference pulse amplitudes. So with a standard single flex probe, you should be looking at like a negative 12,000 to 16,000 millivolts. Whereas if you go with a coaxial probe, it's going to be quite a bit less. So it's good. That's why I was saying it's good to recognize what that looks like on an echo curve. Then you can easily tell if there's something wrong, or possibly even somebody has the wrong probe type selected. That's important for troubleshooting. Some of the things that can affect that reference pulse as well as the radar itself is the way you install this thing. So what we consider a good installation would be something like this, where you have a bushing with a coupling, screw it right in, screw the radar in, make sure it's grounded properly. We consider that a direct mount. So if you're configuring the radar, that would be a direct mount. No need to put an upper null zone normally. That'll work the best. If you put something like this with a tall nozzle and you have different diameters in the nozzle, that's probably not going to work very well. And the lower the dielectric strength of its hydrocarbon, that's going to be a really tough measurement to make. And just to show you some not so good nozzles. Pretty much all of these, with the exception of this one on the bottom right, would be extremely tough to get a good, reliable measurement out of. And the reason being is that microwave signal travels through that nozzle arrangement, and as it sees different diameters like this, it causes a lot of extra noise. When you go through a tall transition like this, you're gonna lose a lot of signal strength when it comes into that open tank. So all these things can affect performance, especially on hydrocarbons. This is just an example of an echo curve that we found that was pretty messy, and we were able to clean it up. So to show you what we did in this case, somebody had used the measure and learn function. There's a feature on the echo curve when you go to pull it up and you go to set the threshold. It has the option to do a learn. Don't really recommend that with guided wave radar, and this is why. Because what it does is essentially just wraps that threshold around all the peaks, but those peaks change. So now you get a threshold that looks like this, and you're going to have a lot of problems from that, most likely. So in this case, you can see from this secondary negative peak here, this was going through a tall nozzle, which caused this peak. Caused noise here. They did a measure and learn, and the interface threshold in this case was set too low. We have a secondary peak actually off the probe end. This is the top of the weight. The positive peak that's being picked up is a false interface. So what we did, first thing, came in, set the threshold straight across. We did a trim near zone. A trim near zone cleans up the noise inside that nozzle. So it cleaned up this positive spike here. And we raised the interface threshold so that it wasn't picking up the top of the weight. So ended up being a pretty clean looking plot. And
so John,
just to show
Wayne, a couple, while we're there, just a couple things that you and I look at. So I look at that reference pulse is usually the first thing I look at, and I make sure that it's at or near zero. If I were to pull these up and look at a reference pulse and it's at 8 inches, it's not at zero, then I know you picked the wrong probe type. I mean, generally, you picked the probe that isn't actually on the device, and it's offsetting it by 8 inches. So that's kind of a ticker for me. If that thing, it could be, an inch off, but if it's much more than that off of zero, it's got a problem. So I definitely look for that, and I make sure it's crossing the green line. Sometimes it's not because maybe somebody's adjusted it, or maybe it's not because there's a super tall nozzle and it's affected that. So I'm looking for, is it at zero and is it crossing the green line? Because if it's not, the gauge has no idea where zero is, and none of your measurements are going to work.
Yeah, that's a great point, Wayne. So that's, again, you should see that reference pulse at the zero. If it's shifted over a foot, either way, it's a dead giveaway. You've selected the wrong probe type. There's also some instances where you'll have a remote cable, and if you don't select a remote cable but you have a remote cable, that'll really throw it off. And again, if you look at the amplitude, this one's kind of hard to read, but it's maybe negative 9,000. It should be a little bit stronger, but it's not because of this secondary peak. So going through that tall nozzle created this peak, and it took energy away from the reference pulse as well as the overall measurement. So anytime we can lessen those nozzle effects, you're going to have a much better reading. Some examples of some plots where we had issues. This one was actually a bushing, so it was a good installation, but it got packed up with I don't know, some kind of paraffin or something, and it plugged up the nozzle. So open up the echo curve, your reference pulse should be negative and it's positive. That's telling you that's a dead short. So something pulled it out. It was just packed. So we cleaned it up and then it started working. Quick way to tell if it's a bad connection between the head and the probe is you'll get a super strong reference pulse and basically no amplitude for a surface. That's telling you that you have either a bad connection, or it could even be I've seen where they've contractors have gone out and installed the probes on top of tanks and came back a week later to put the heads on, and they let them sit out in the dirt with the dirt blowing on them and the rain and whatnot. And now all of a sudden that connection, that spring pin connection, got dirty. That's really all it takes. So we have to protect that connection. Emulsions. This is a really good example of what an emulsion would look like. And Wayne, I have this plot, if I can get it to play here and you want to speak to this. So I have actually a live echo curve.
So this echo curve, you're going to see it really fast, but it happened over about 20 minutes. So, John, if I can get you to go maybe just, I don't know, a third of the way into this, or a quarter of the way in, just. So what we have here is there was a slop tank that when they run a pig through their pipeline, everything goes into the slop tank. They let it sit there for a little while, and then they turn on a transfer pump and pump it over to this separator that has a weir in it. So you'll see the surface level. Probably go back a little earlier on the plot, John. Just maybe a quarter of the way. Yeah, about in there. So you'll see that surface echo. Yeah, maybe even go back more. You'll see the surface echo start coming up when they turn the pump on, and it'll come up until it hits the weir. Okay, now you're into it. So, okay, they turn on the pump, just start inching forward. You can see that level is coming up, and it comes up until it hits the weir. Now it's spilling over the weir. You can see our interface back there, and I want to stop 1 second on this. So notice where the levels are reporting is where the arrows are at the top of the screen. It's not necessarily reporting where the peak is. So it'll always be where the arrow is. So that's our level, and that's at the height of the weir. Our interface is that kind of pink arrow. Right, that's where the interface is. So there's already water in this vessel. But again, as they keep the transfer pump on and we keep going forward, you'll see pretty soon we start pushing water from the slop tank into this separator. So that level starts going up. And then I want you to watch the amplitude of that. So see the little trail of dots? You can see it's kind of going down. It's going down some more. Going down some more. Stop it right there for a second, John. So at this point, we've got a big emulsion in there. You can see that it's got sort of two peaks. It's having a hard time where the line with the little square on it is. Having a hard time identifying where is the peak. Do I want the left one? Do I want the right one? Do I want in the middle of the two? If you notice that vertical line where it says P2 interface is jumping all over, but the arrow isn't. So what the gauge is reporting is a pretty steady point for the interface, even though it's having a hard time deciding exactly where that interface level is. So you'll see that jumping around. Even a couple times it loses it and doesn't report, but it keeps reporting where the arrow is. It keeps giving us the interface. Now, if you look at that interface amplitude, it's less than the hydrocarbon surface, right? It's well below that surface. So what we noticed that day, we said, wow, you go very much further. You're going to be pushing emulsion into your oil tank. So what's the right solution? And we said, all right, shut your transfer pump off. Just shut it off and stop. And let's wait until the amplitude comes back up as this separates. So you can shut it off the pump, let it separate in here, and we actually put logic in the program to where if it gets below about 4,000, we stop the transfer pump. And you can wait till it gets above 5,000 before you turn it back on. So that way we're not ever pushing emulsion into the oil tank, right? We know we have a good oil-water interface. So go ahead and just click ahead a few more, John. You'll see there, it doesn't quite know, but look where the arrow is. It's still reporting the interface where it was. Because it knows it's got to still be about in that vicinity. It's not going to move feet in 20 seconds. So it doesn't quite know what to do, but it catches it back and just keeps on reporting. One other thing, if you notice our blue interface line, that's set up to catch our oil surface peak, which it's doing really well. The surface peak is well above the blue line. Why do you think we lowered the interface threshold, the pink line? We put it right at the same spot that the blue line is. Well, the reason is we knew they were getting emulsion, because what the operator reported was, I'll start this transfer pump, I see the oil come through, I see the interface level, and then all of a sudden I lose the interface level. So what's happening is that pink line, we had it set higher. It was up about 4,000. And when this emulsion would come, it's below 4,000, so it wouldn't recognize the peak, and they'd lose their interface peak. So now they have no idea where the interface is at. So since we knew they were playing with emulsion, we just lowered that interface threshold down to 1,000, so it will always catch the interface peak, even if it's emulsion and it's sloppy. But again, what we opted to do then was take the amplitude of the interface peak and put that as an output back to the PLC so they could start and stop the pump with that. So if they're pumping and it gets to be emulsion, pump shuts off. Once that amplitude gets too low, then it waits till the amplitude gets high again before it turns back on. And that just really cleaned things up at the site where they weren't getting oil in the water tank and water in the oil tank. So, John, go ahead and just click through to the end.
Yeah, that's a great point, Wayne. So you can, both of these peaks, so the signal strength of the level as well as the signal strength of the interface, you can bring those in as one of the variables for the radar, and you can monitor that. So hydrocarbons should be, 2,500 millivolts or less, and water should be 6,000 millivolts or more. If those two start getting off, if you see the water way down here at 2,400 millivolts, there's an emulsion. That's one of the nice things about radar. If you can learn how to read the plot, you can quickly, if somebody pulled this off, you could tell right away there's an emulsion in this tank, without a doubt.
Well, yeah, and even just from the operator's description where he says, I've got good interface, and all of a sudden it's just gone. I'm like, okay, well, you're going below the threshold. So before we even started this plot, I did one thing. I went in and lowered the interface threshold so it's down where the blue line is. I said, all right, now let's turn it on and record for 20 minutes while you're doing a transfer, and let's see if we can tell what's going on. And by just sitting there watching the screen while they did the transfer, it was super easy to see, oh, well, that's an emulsion, and now it's getting too low. And we would have lost it right there because it went below 4,000. Really easy to tell what's going on as we just watch this. And this was giving us a plot about every 20 seconds. So it gave us a pretty good view into what was happening in that process.
Yeah, that's probably one of the best examples of an emulsion plot that I have that you sent me. were here. So if you had a tall nozzle on a tank, like some of the pictures I showed previously, you have a water tank. So a water tank is going to give you that really strong reflection. You can see this will be a water reflection. You can see the amplitude is way up here above 7,000 millivolts. Well, that peak is so strong that you get a double bounce, we call it. So you get a double reflection. It's exactly, if you go from 0 to the distance of this peak and go double that, you'll have another peak. And if you extended this echo curve out, it would just go on forever. You have another double and just so on and on. So what can happen with a nozzle is it throws off the radar's ability to detect whether or not it is a double bounce. So if you have the interface set down here around 2,000 or 1,800 millivolts, where we typically put it from the factory, a double bounce can sometimes be picked up as a false interface level. And this is kind of what you would see here. So really, in the older versions of our radar, the only way to fix that would be to grab that interface threshold and raise it up higher above this double bounce so that it doesn't pick it up. So we have a fix for that now. But if you have an older version of our radar, say older than 2 years old, chances are if you have a tall nozzle, that you're going to have this problem. This is an example of a probe that was inside a tank, and it was right up next to a metal bracket. Number one, they had the threshold way too low. They had it at like 150 millivolts. So we were picking up just a little noise spike at the top, which was a false level. And then once we fixed that, we were still picking this peak up, which is a false level too. And you can tell usually if it's metal or something like that, because you'll get a positive return followed by a really sharp negative return. That's usually a dead giveaway that it's not a product in the tank. It's probably a metal bracket. And you can see the amplitude is around 5,000. So that's not even close to what oil should be. So some of the things that can really affect probes. So paraffin, heavy coating, bridging. This is why we don't normally go with the dual flex probe anymore in oil and gas, because you get this kind of buildup, and that shorts out, causes a false level. The best option is our single flex probe. It can handle a lot of buildup. For the most part, I've even seen some that had built up almost 4 inches in diameter, and the radar's still red. It just lowers the amplitude. So you lose signal strength by going through that. And it can offset your measurement some, because as it goes through that buildup, it slows it down. So now your accuracy can be thrown off too. Same thing here. If you look at this probe, it's just coated up with paraffin. For your signal strength, you're still going to make a measurement. It's going to weaken it some. You're going to lose signal strength, amplitude. But what it will do is cause your accuracy to be off. So those are things that can affect that. One of the things that we have that's a good preventative maintenance tool you can put on the radar is it's called SQM, or signal quality metrics. If you set one of these up with the signal quality metrics on a new installation with a clean probe, you'll get a number value. It's normally close to 10, say 9.5 to 10. Over time, if you start getting buildup, or the ratio between the signal versus the noise gets stronger and stronger, that SQM number will start degrading. So you can set this thing to alert you at, like, say, a 7, and it'll tell you ahead of time, hey, you need to think about going and cleaning this probe maybe in a month. So you're not just out there pulling probes out and cleaning them for the heck of it. We also have a way to verify the radar now. Call this a verification reflector. You also hear there's another word for it, high-level supervision. But what this does is we put an actual kit on it, a bracket that we clamp onto the probe itself. It's a software addition to the radar, but you can go in and calibrate it, and it calibrates the radar to that fixed distance. So again, this is an impedance change, kind of like hitting a different surface would be. It knows where that impedance change should be. It's calibrated to that point, and then you can come back, say 6 months down the road and check it, 3 months, whatever, and it's actually going to run that signal down and verify that it's still, the amplitude is still the same, it's still in the same position, and that the radar is still functioning properly.
So, John, can you do that on a gauge that's doing level and interface, or does it have to be a gauge that's just doing level?
It would only do level. But you could still do it. It's a way to check the radar, but it's not going to check the interface. Is that what you're asking?
Well, yeah, I was just asking if I could use it on a tank that had oil and water, or if it's just going to be like a water tank or an all oil tank. I didn't know if you could read that reflector and 2 more surfaces.
Oh, yeah. If you look at the echo curve, the reflection you get off of this, it's pretty small. It wouldn't be anything like a peak off of the oil surface or anything. It's just it's a really small, kind of like a reference reflector on a DVC probe.
Okay.
We have an oil and gas configuration. I highly recommend. We're still using the R number here for Rosemount. It's a R8188. That's our way of saying upstream oil and gas configuration. This is free. If you're putting this on an upstream oil and gas production tank, water or oil, I highly recommend it. And if you have a direct mount, like we talked about earlier, that doesn't have a nozzle, it's a direct mount, and you're doing product level and interface level, this pretty much sets everything for you. There's a handful of parameters you have to go in and set. One would be the tank height, probe length, the ranges, and the tag. Everything else is here. You don't need to really change any of this other stuff. And what it does for your thresholds is it sets them, and we've over thousands and thousands of radars we've looked at. This is kind of like the sweet spot. So it'll set the level threshold just like this. It'll set the interface threshold just like this. And unless you have a tall nozzle or something to that effect, this is going to be perfect for you. You shouldn't have to really change any of this. So it makes it a lot easier to configure the radar. And then just wanted to mention this real quick. So once you have the radar installed, you have it configured, you have product in the tank, one of the things you normally do is you look at the radar output versus a manual measurement. So hand gauge, tank strap, whatever the word is where you're at is called. But to do that on the radar, there's a function you can go up, and it's called verify level. So it'll show you what the radar is reporting. And then if it's off, say a half inch from what the hand gauge is, you can put that value in and it makes that correction for you. It used to be you had to go in and put an offset manually. It was a little more involved. This makes it a little easier. And the things that can make it off from a hand gauge measurement, keep in mind this radar is very accurate, right? But your tank height that you enter, it uses that. So it takes the tank height minus the distance to the level, gives you a level. So if your tank height is off by half inch, your level's off by half inch. So that's where you can run into discrepancies. Also, sometimes where you gauge, where the pumper, whoever is gauging the tank, drops the strap into the tank may not be the same position that the radar is sitting on the flange. So you have to adjust for that too. So once you get the overall level dialed in and it's matching perfectly, your interface, that'll be the next thing you check. Let's say if your interface is off just a little bit, our default is 2. So we use this upper product dielectric constant. We use a 2, which is kind of like the pretty close to the mid-range. Normally that's really close, but if you have to tweak it a little bit, your interface is off, say 1/4 inch, half inch, you can adjust this. And there's even a calculator you can use. But that number brings in your interface. So if you do verify level to get your level matching, and then tweak the upper product dielectric, that'll bring in the interface. Just to tell you a couple of the new things we have with the radar. Previously, to be able to do level and interface, you had to have around 5 inches of upper product thickness. The reason being is that lower dielectric, if it was too thin, the radar just shot right through that and hit the higher dielectric, the water in this case. So you had to have at least 5 inches to be able to get 2 peaks. Well, now we have it's called a peak and peak solution. So we have a way to measure really thin interfaces now. If you look at, this is not the greatest picture, but the picture on the left would be, this actually has oil and water in it, but it has less than 5 inches of oil. So all you see is this big water peak, right? Not strong enough to separate out, not enough product thickness. The one on the right is what the new one looks like. So it's almost, that's why we call it peak and peak. It picks it up, and you can't really see it on the plot, but it's picking it up. So we can go down now with a single flex probe. We can go down to like 2.4 inches of upper product thickness.
And that's not something you special order. Just all the gauges that we ship now, all the 5300s have this ability, right?
That's correct. Yeah, you have to enable it. If you do the R8188, it's already enabled for you. If not, you have to go in and just check the box for thin interface detection. And it's only available on certain probe types. So if you try to set it up on a dual rigid probe in a chamber, it's probably not going to work. So it's meant for single probes, and also we can use it with a large coax, which we can get down to even 1 inch of upper product thickness with that one.
So, John, I want to talk a little bit about the graph on the left, the legacy stuff. So one thing that you would see in the control room or back on your SCADA system is right now it's reporting one level, and it's, we think that's the top level, right? Well, then all of a sudden you get, 6, 7 inches of oil in there, and all of a sudden it can actually detect it. You'll see the level jump from where it is now to, 5, 6 inches higher than where it is now. So you get this real jumpy effect on your level trending, because sometimes it'll break out and it can see that, 6 inches of oil. Then you skim a little bit, it can't see it anymore. The other thing to note is that this water level is actually not accurate, because you have some oil on top that it's not reading. In fact, it's slowing the microwave down a little and makes the water level look even lower than it actually is. So in that case, you're not getting a top level, you're getting a water level that's probably a little bit artificially low, because you don't have enough oil there for it to detect it. So this really, the new version enhances the accuracy significantly of both the water and the oil peak, because we can see a lot smaller pad of oil. That makes sense?
Yeah, absolutely. I wish
Hey,
I had
John,
Yep.
can you zoom in on the thin layer plot there and show those 2 peaks a little clearer?
I want to say yes. Let me see if I can figure out how to zoom this in. Is that better?
Yes, sir.
Just not too blurry.
Now, compromise between clarity and blurriness, clarity of the message and blurriness of the image.
Gotcha.
So to your point, you still don't see 2 peaks here, but the radar is able to determine that there are 2.
Correct. Yeah, if you're used to seeing, like you said, 2 separate peaks and then they kind of merge into one, and then you don't see it anymore. It's a little weird looking at first, but it actually works very well.
And then also, didn't this latest firmware get rid of that echo problem on the water
double
tanks?
bounce. Yeah.
Yeah.
Yep, that's sure. So that double bounce problem's been fixed too. That's what I was saying. If you do the oil and gas configuration, you're perfect. The thresholds are perfect because you don't have to worry about raising it to avoid the double bounce. You still could have that emulsion problem, but we set the interface threshold from the factory at 1800, so that's usually pretty good. If you're going less than that, then you really have a bad emulsion like you showed earlier in your plot. And for those of you that are familiar with the radar, say 3 years ago, you had to select thin layer on top for a water tank, thin layer on bottom for an oil tank. That's been corrected too. So now you can just leave it at unknown because it doesn't matter. It doesn't use that function anymore anyway. Okay. So now it's question time. Hopefully there are some questions.
All right, I'm going to go ahead and unmute everyone. I am going to ask that if you're not speaking, to please mute yourself to cut down on background noise. But here we go. You can ask questions that you've come up with.
John, you may want to go back to a plot, just so we have a plot on the screen that people can ask questions about.
Hey, John, this is Todd Bryan with Chevron. Can you hear me all right?
I can, Todd. How are you doing?
Real well, thank you. Good training, good presentation. The first question I had, I actually put in the chat, but I'll ask you directly here. With the pump permissive, the emulsion example you gave of the emulsion and using the interface amplitude, was that assigned as a heart variable and stripping it out as a heart variable at the PLC card?
Yeah.
Yes, it was.
Exactly.
You have 4 heart variables, so we did level, interface, and then we actually only did amplitude of the interface. So we were just using 3 variables, but they did have a heart card, so they were able to read all 3 variables.
Okay, very interesting. Yeah, that's we bounce into that a lot, and I guess the other thing that was an eye opener here was the firmware update. Now, I wanted to ask a question. You showed legacy, cables, where we have the 2 cables going down. We do have some of those from all the 3300 series, but when you talk about thin layer, did you say you get more if you do a coaxial probe, or you can actually still do that with the single cable?
So with the coax, we have a new probe type called a large coax. It's almost double the diameter of a standard. It's like 1.7 inches diameter. Okay. And it has, instead of having holes in it, it has slots. And so there's no space on that entire probe that doesn't allow fluid into it. So if you use a large coax, mostly in like a chamber application, I'm thinking, you could go down to like 1 inch of a product thickness with that one.
Okay.
So with the single cable, it still goes down to 2.5 inches. So it's half what it used to be.
Yeah, kind of our rule of thumb is we tell operations try to stay above 8 inches. As a rule of thumb, we say, hey, if you're skimming levels and everything, whenever you get to 12 inches, stop it, right? So this is pretty compelling. So does this require the firmware update if we want to put this in some of our older 5300s?
Yeah, to get that thin interface would be. So the latest firmware now, I have a demo here that I'm connected to. If you can see my screen, this is the 2L3. The 2L3 has that thin interface, as well as all the other things we talked about. The most recent version now is like 2M0, but the 2L3 has everything. So if you have 2J0, then it wouldn't have it.
All right, and I'm just going to ask some generic questions. How does one update the firmware?
You beat me to it, Todd.
So it's pretty involved, actually. The firmware, you have to, You have to take the head off the probe. It has to be in a controlled environment. We have a programmer box that you have to load the software. It's a pretty involved process. Normally, it's going to require one of our service techs to do it. It's not
All right,
just
Karl, this is kind of reminiscent of the center pin replacement and firmware upgrade where they brought a contractor out here to all of our areas in Colorado and did that on site. So it's pretty entailed. Then it's not something you just whip out of Trex and perform, huh?
That's correct. Unfortunately, yeah.
All right. No,
Yeah.
Fair enough. Thank you. I appreciate it. Thank you for the training.
Yeah, absolutely. Thanks for the questions. I was just going to show for anybody else that hasn't seen this, so what we were talking about. So if you wanted to map the signal strength of this interface peak, in this case, it's like 5,000 millivolts. You could go in and assign it as one of the variables. So we could do it, well, in this case, we're doing level, interface level. This will be your signal quality we talked about. You could also map that as a variable, as well as you could put that on the display. So even if you didn't have the means to bring in another variable, you could have it flash on the display, and a pumper or operator, whoever could walk by, look at that, get them used to seeing that number. Say it starts out at a 10. As it degrades over time, they see it's a 7. So, hey, we need to think about getting this thing clean. So that's something that could be put on there. Signal strength, you have the level, and then you have, that'd be your interface signal strength. So you can bring that in, and that's going to show you the amplitude of this. So that's how you would monitor that.
Yeah. Okay. Thank you. That's very useful. I think that's probably one of the biggest takeaways that I had from the entire training, because we are oil and gas, and we do run into that emulsion issue quite a bit.
Yeah. Great.
Hey, John,
Yep.
maybe you can step us through how to set up a recording over time on a plot, and then also how to save that file and be able to email it to me or you or Wayne, or to the techs at the factory or whatever.
Yes. Yeah, certainly. Let me zoom in here a little bit. Okay. So when you're looking at the echo curve, normally you're not going to see, let me get rid of some of this stuff here. This is kind of the default. This is what you'll see when you pull up an echo curve. I like to go and include the table, which gives you the distance as well as the level for your level and interface peaks. And then it gives you amplitudes, and it even gives you the amplitude of your reference peak. So I include the table on there. If you do the echo peak trail, it'll put the dots. So every time this echo curve updates, you'll have a dot. So you can track this over time. Like say you're filling this tank up, it'll just have dots going like this, and it tracks. So you can see what the amplitude's doing. I usually enable that too, and I'll put the labels on there so it shows everything.
On that plot we were showing had the dots. I had that turned on when I recorded.
Yeah, that's exactly what it was doing. So it's a good thing to have on there. So you have 3 tabs on here. The first tab is configuration mode. This is where you can set your thresholds. If you just wanted to set it straight across, you would just come over here and say set threshold. This is just a generic default number. Let's say I wanted to put it at 1,000. Just punch in 1,000. And now it's going to tell you you're going to overwrite the automatic threshold settings. Do you want to do this? You say yes, and it'll change it for you. This learn button is the one over here to the right, bottom right next to set threshold. That's the one I was saying don't use. We were actually going to remove that from our guided wave radars altogether because we don't recommend it. So that's how you would adjust the threshold.
So John, once this thing updates, show them how you can just adjust an area of the thresholds.
Yeah.
Like by grabbing the bubbles.
Yeah, exactly. Like you have a permanent metal piece that giving you a false echo.
Yeah, I don't have anything to make a false echo. Let's just
raise it over that little hump on the left. Yeah.
You talking about this one?
Yeah. Yeah. Just raise those up a little bit.
Yeah. So normally what I like to do with an echo curve is I put my mouse wherever that echo curve sine wave is, and I look at the amplitude. So this is 500 roughly millivolts, and I put it where the level threshold is. I like to keep a 500 millivolt spacer in between, right? Because that allows for temperature changes and fluctuations. This peak could increase a little over time due to temperature and whatnot. So I try to keep 500 millivolts in between. So in this case, I'm actually pretty good. But let's just say I wanted to go more. Zoom back out. I could just click and drag the dots like this. Wrap it around and then just hit store to save it. So what's nice about this radar and this software is you have the ability to do that. Learn will kind of do the same thing, but again, it just wraps it around everything like this. And that's why you don't want to do learn. But like if you had a fixed metal object, say right up here at the top, and it was giving you a positive reflection, you could just click and drag the dots around it.
Well, and as you zoom in closer, you get more dots. If you're zoomed out, there's not very many dots. You zoom in, you get more dots. You zoom in some more, you get more dots. Right, and then it becomes easier and easier to get it the way you want it.
The only
and then
time
show them
this
how you
becomes,
move the. Oh, sorry, I was going to say show them how to move the interface threshold. I'm not sure everybody knows that.
Yeah, so there's a couple different ways. Probably the easiest way is just click over here on the bubble and drag it. Just drag it up to where you want to put it. Say the factory default, if you do the oil and gas, it's going to be down here at about 1800 millivolts. It'll be right about here. The level will be 1000 and then step down to 800. One other thing to note, if you do have that oil and gas configuration, like on my screen now, I have a green check over here to the bottom left that says online, and then I have another one that says device status OK. This device status OK will not be green anymore. It'll be yellow, and you'll have a warning. And what the warning is telling you is that these automatic tracking settings have been disabled. So you're going in and manually setting all the thresholds. That's why you get the warning. There's nothing wrong with the radar. It's letting you know that. So if you have the oil and gas upstream config, you'll see a yellow right here.
Yeah, and that freaks a lot of people out. They're like, "Oh, what did I just do? I must have broke it."
Yeah, there's something wrong. Yeah, I don't really know.
There's nothing wrong. It just means you overrode what the factory guys thought you should have in there.
so before we leave this, one bit of warning: when you move that blue threshold, if you should come with an echo that needs to break that line where it would have normally been, if it's below where you raise those dots up, you're going to lose your level there. So be very careful when you're doing that. Make sure that it is actually something that is an obstruction and a continuing problem at that exact location, because you're going to lose your surface if you're raise that up too high.
Yeah, that's a good point, Carl. One other thing I didn't mention earlier, but I should have. So two things affect amplitude of your surface. One is the dielectric constant strength, the signal strength, and the other is distance. So if you have a peak, let's say this oil peak was down here at the bottom, and you are reading 2,000 millivolts signal strength, it's only going to get stronger and stronger as it goes up closer to the top. If it's 4,000 millivolts up here and you're basing your threshold on that, you need to be cautious because it's going to weaken as it gets lower and lower into the tank. On a 20-foot tall tank, usually not a big deal. On a 100-foot tall tank, big deal. If you try to set your threshold based on the level way up here, it's going to be a lot lower when you get towards the bottom. So just keep that in mind. So again, configuration, this tab, you can make all your changes to the plot. To zoom in, you just use left click, kind of do this. To zoom out, you right click, zoom out. Talking about the red line, this is that upper null zone. You can change it by clicking and dragging it, or you can do it in the configuration. I usually do it in the configuration. So it'd be right here where your probe is. You put the probe type, probe length, and then if you needed to add that upper null zone, if you have a nozzle, really, if you're direct mount, I don't ever mess with that. This would be where that use spin layer detection would be on the environment tab. Again, if you have the 8188 oil and gas, this will be set to unknown, typical interface. This will be checked. This will be to your upper product dielectric.
Okay, so show us how to record the plot.
Okay, let me store this. So anytime this screen is yellow, it means you didn't store something. So I need to go back and store it first.
So while we're here, John, there's one thing weird on your plot. I don't know if any of our viewers noticed, but where is your reference threshold?
The reference threshold?
It's not at 0. Your reference peak?
Oh, the peak. Yeah.
It's not at 0. So that's one of the first things I noticed when this pulled up. I went, not at 0. So
look
something going on there.
So I have a flexible single probe selected, but in reality, I have a dual rigid probe. That's what my demo is. So that's why it shifted it over.
So again, you could tell immediately the probe type you've told it is not what's really on the gauge. Yep. Right? That was a dead giveaway.
Yeah. Excellent. So let's say you have the plot set up, or you want to send us a plot like Karl mentioned to have us help you troubleshoot. You go to view record. Now from this tab, you can either click this button and it'll sit there and just update over and over and over until you stop it. Or if you want to record it, it's the red button. And you have to be careful here because it gives you two options. You can start recording and it'll record as long as you let it go until you stop it. I've had frames that were like over a week long somebody sent me. Or you can just do a snapshot. But normally we ask you to send us like 10 frame file if you can. So I would say start recording, and you want to put it where you can find it, because if not, you'll never find it. Radar Master saves it somewhere that you'll never find it. So usually I do like desktop, and I would create a folder. You can see I'm good at creating folders. So I'd put a folder of the location and all that. It saves it with the serial number, the tag number, and everything for you. So again, I don't have a separate folder, but I'll just put it on the desktop. I'll say open. You can even put a note here. You could put during fill, or
like as found, or you do oftentimes an as found and then an as left if you changed it, right?
Or like you did earlier with your emulsion example, Wayne, you could say, well, we were putting product in or something. Yep. And you save it, and it's going to sit here and record it. You can see it put the note up here for you. It has the tag number, has the serial number, firmware version. and it'll record until you stop it. If you had to like try to catch an issue and something that happened intermittently, then you could, if you had a way to connect this up to the radar and leave it running, you could let it run and plug your laptop in and let it go. It'll go for almost 2 weeks before it runs out of memory.
Now, the bad part about it is you're getting a snapshot about every 20 seconds. So you're not seeing like full speed real time. So if it's just a little intermittent blip, you might have to track for a while before you see it because you got to catch it on one of those 20-second intervals.
That's right. It runs at the speed of heart, so it's not super fast. But I usually let it go about 10 frames and then hit this button to stop it. So it saved it to my desktop. If I look for LT5000, good luck on this desktop. But actually, here it is. I can't do it because I have it open. Hang on. So now I can go back and play that plot that I just saved. Not much to look at because it's 3 frames, but if it was a longer one, it would actually show it. If the level was moving, it would track it, and you could troubleshoot that way.
So one of the things that John and I ask a lot, if you're having a problem with the radar, the first thing we're going to say is send me a plot. So if you can go into that view record, do a snapshot and send us that, that's great. A lot of times, guys out in the field doesn't have internet access, might be the end of the day or tomorrow before he can send me the plot. Worst case scenario, take a picture of a plot with your phone and text it over to us, right? So it's a little bit harder for us to see. It's kind of hard to read the scales, but generally by looking at the shape of the plot, we can tell you what's wrong. There's the classic, right? You can see the guy taking the picture in the bottom of in the reflection. But we get this all the time. It's like, okay, just send me a snapshot of it and that'll give me a starting point. I'd rather see this than any of your config stuff because I can generally tell how you've configured it just by looking at this.
Yeah, this was a quick and easy one. I mean, raise the threshold. Something's going on here, verify there wasn't a metal object, which he did. And he said, yep, there's a bracket about 10.5 feet down. I said, okay, get it away from that, which he did, and then everything looked fine after that. So this was an easy one, but that's all that this guy did is just took a picture with his phone and sent it to me, texted it.
Yeah, that's probably the most common output I get is a picture from a phone. It's nice if we have a file, we can do a little more with it, but yeah, you can usually do quite a bit just from a picture.
Yep, good point. And so the backup, if you contact our factory, they're going to ask you 2 things. They're going to ask you for a plot. They're going to ask you for a backup for the configuration because they want to know exactly how you configure the gauge, right? So to do that, you just go to device, backup config. Again, if you had a folder already with your echo curve, it's probably the easiest way to do it. Which I'll just use the same tag, but you have to take the DAT off of it because the DAT file is the echo curve and the BAK file is the configuration. So I would just save that. I'm not going to do it now because it takes about 5 minutes. But so those 2 things, and we can easily help you.
Let's talk about what's your preference about setting up a radar? Do you want anything in the vessel? How much? What about setting up in an empty vessel?
Yeah, so a couple things you need to be aware of on an empty vessel. Empty vessels have noise. A lot of times you'll see the signal look a little noisy. That's normal. As soon as you get product on it, that noise clears up. But one thing you need to be careful of, if you do this trim near zone, you don't want to do that on an empty tank. If you do it on an empty tank, a lot of times that noise will amplify it when you do the trim near zone. So I always say get some product in the tank, but make sure you're at least 4 feet below the top when you do it, because you don't want to risk trimming out anything, because what it does is trims out the top meter. If you do a trim near zone, the level's up in here, you're going to trim the level out. So you got to make sure the level's below that, but you do have some product.
So I'll say in my experience, you set up an empty tank, you go with these R81, 88 sort of defaults, adjust your reference height depending on the actual tank. And then it's probably not going to be all the way right. It's 90% right. Once you get some product in where you can actually, verify the level and the noise goes away, then you can just fine tune it and you're done. And then you should never really have to touch it again. But it's super hard to make that claim on an empty tank. On an empty tank, you're probably going to go back when it gets product in it to finish setting it up, to dial in your top level exactly right with a hand gauge and all of that. So it's empty tanks. Gauges don't like empty. They like to read a level. And if there is no level, they kind of generate noise.
Yep. One other thing I was going to say. So I don't have an example of that, but if you had a single flex probe in a tank hanging down 20 foot, you had a weight on the end of it, a lot of times you'll get a positive peak off the top of that weight. And sometimes it can be strong enough that when it's empty, that it'll pick that positive up as a level. So you'll get a level reading about a foot down here when the tank's empty. What I do in that case is I would just take the dots, again, from the configuration, and just, let's say there was a peak right here, I would just kind of drag the dots right around it and then store it. So as soon as the level gets into the tank, it's going to be stronger than that reflection off the weight, and it'll start reading. But that's very common.
So there is one thing we didn't talk about at all, and maybe that's beyond the scope of this one, but there is a thing called probe-in projection. And if you're in a tank that's strictly hydrocarbon and you're having a hard time reading the level, like a propane tank, you can actually read the level off the apparent length of the probe. The actual length of the probe. When you put it in a hydrocarbon, it slows the microwave down, so now the probe looks longer than we know it actually is, and we can back calculate and tell you what the level would have to be for that to be there. So I've used that in some specialty tanks like butane, propane, that sort of thing. You can't use it in a tank that's got two products. It's got to be a hydrocarbon product only so that you can see that into the probe. But there are some cases where that makes a better measurement than trying to get the noisy surface. If you're in, a gas plant with a chiller, you may, in fact, as you're lowering the pressure and open the valve to let the propane circulate, it drops the pressure and it starts boiling, and you'll lose your surface level if it's boiling. But you can do probe-in projection and you won't lose the level. It'll track it even when it's boiling because it sees how long the probe appears to be, and then it calculates the level. So it's got some horsepower to do weird stuff. If you get into goofy applications like that, we can do those with this 5300, and it's really hard to do it with any other radar.
So with probe-in projection, though, correct me if I'm wrong, if you didn't turn on probe-in projection when you commissioned the thing and you decide that you want it later, you have to empty that vessel in order to turn that on and have it work correctly. Isn't that right?
Yeah, so if you think you might have that issue, particularly if you're in a gas plant and you're going to have, a pure hydrocarbon, when I put the gauge in and the tank's empty or the bridle's empty, I'll run the calibration on the probe end, even if I don't plan on using it. Because if I come back in 3 months and you guys are having weird problems and it hasn't been calibrated, yeah, we get to empty the bridle or the vessel. So if I'm going on an empty one and I know it's pure hydrocarbon, I'm going to calibrate that just in case I need to use it later. Doesn't hurt anything to run that little cal routine and, and get it set up. Then if you want to use it later, you just go in and check the box and you're up and running. So I do the calibration generally. If I'm in a place where there's any conceivable way I might have to use it, I'm going to calibrate it when I put it in and the tank's empty.
Yeah. Boiling hydrocarbons, like you said, propane, butane, really like spear tanks or whatever, those are usually probe and projection applications.
Yeah, it just gives you more ways to solve the problem if you're having a problem.
What about some minimum design considerations when you're putting a radar in a chamber? Since you mentioned boiling hydrocarbons, because I see that a lot in chambers, especially when they're too small.
Yeah, we like chambers to be 3-inch minimum. We really prefer 4-inch. What we see a lot of guys in the field do is make them 2-inch, and that's difficult to make a radar work in a 2-inch. If we're in that situation, we'll probably put in our large coax so that we can kind of control how that thing works. But we'd much rather have a larger chamber, a little more surface for the gauge to read. We also like about a foot above the top connection and about a foot below the bottom connection, so that everything between the connections is in a good measuring range for the radar. So we see a lot of guys will build, if they're building their own bridle, they'll connect at the top and then 2 inches above that'll be the flange. We like that to be like a foot. So we're down in range where we can really measure. It's hard to measure right up near the flange. We have actually a write-up on design on these things if you need it, and we pass on to engineers. We have one for stilling wells in a vessel as well, just kind of a best practices on how to build those. John, you got anything to add?
No. Just hoping there was some questions.
We would rather build the chamber with the radar, because then we know it's going to be right. We'll make all the dimensions right so that the radar can read, between those process connections really well. But sometimes we got to work with what we've got in the field.
Yeah, I'll make one comment about that as far as the factory chambers. I think it's been probably almost 3 years now, Karl. You helped us. Emerson acquired Magnetrol. Is that no
Magtech.
Magtech, right? The magnetic flip indicators. That was really interesting because I did mention Magnetrol because we've got a good many of those in some of our areas. But they have that Aurora or Orion combination with the guided wave radar. Not very successful, in my opinion. But the Magtech and 5300, the options that you guys have are pretty good options for those folks that want to have those magnetic level gauges and a guided wave radar together. And we haven't had any problem with that. And like I said, I think it's close to 3 years.
Yeah, and our experience with that is way better to do that in 2 chambers. Trying to do all that in 1 chamber doesn't give the radar much room to work, not much surface to read. And we've just found that we have a lot better success if we put the magnetic flippers in 1 chamber and the radar in the other chamber, and then just have the chambers tied together. That, for us, that tends to be pretty bulletproof.
Yeah, and that Magnetrol uses a 3/4-inch diameter coax, so it's a really small probe to begin with. It works well on clean products, but if you have any kind of buildup or dirty process, it doesn't usually fare too well. One thing to note on that, so keep in mind, if you have a radar in a chamber and you have an MLI built in, like a combo 2 dual chamber, the magnetic level indicator has a float that works off density. So it's calibrated to a specific density. And that's how that float tracks. So the flippers that you see, the indicator follows that float, right? So if your density, if it's calibrated for a 0.8 density, but the density is 0.5 for some reason, it's not going to be accurate. Where your radar doesn't look at density, it only looks at dielectric. So radars are not affected by density changes, but that float is. So just keep that in mind. If you're running outside where you normally would be, and an operator sees that indicator and says, hey, man, this thing's not matching the radar, the chances are that's probably why.
Yeah, John, I've had a few cases where they've said that. They go, well, look at the magnetic level indicator. It says the level is, 6 feet, and you're saying the level is 8 feet. And you take your infrared thermal gun and you shoot up and down the pipe that the MLI's in, and you can see the temperature change, and it's right where the radar says the level is, right? The float isn't floating where the level is, but
right.
Yeah, you can usually tell by temperature change right where that level is, and you go, yeah, your float's not floating.
Yeah, radars don't lie. If everything's right on the radar, it's configured properly, you can look at that distance to the peak, and it's usually spot on. It doesn't give you false readings normally. Where a float or anything that works off density, it's always calibrated to a specific density. If the density's off, it's going to be off. There's nothing you can do about that.
So I'm going to second or third that opinion on accuracy of a radar. Operators tend to want to blame the equipment. And I think that that's a natural human tendency, because if they don't understand how it works or whatever, that's the thing that's going to be at issue. Those of us that are techs, we tend to believe the instrument more than the operator. And I would say 90% or higher of the time we're right, and there's something else going on rather than something wrong with the instrument.
Well, Carl, for instance, I can't tell you how many times I've gone out and I go, oh, yeah, it looks like you got 6 feet of oil and 10 feet of water. And they go, no, that's a water tank. There's no oil in that. And I look at it and go, yeah, there is. There's about 6 feet of oil in that. And they absolutely are convinced there's no oil in the water tank, but you can see it on the plot, and it's obvious that there's oil. And you have them thief it, and sure as hell, there's oil. They just didn't know it was there. And they didn't want to believe it was there. But yeah, you can usually tell looking at the radar plot, is there oil or isn't there oil? It's pretty obvious.
Yep, that's what I'm saying. The radars don't lie. They show you what's in there, and based off dielectrics, you can expect certain amplitudes off the product. But you can tell there's, like in this plot, if I was looking at this, I would, without a doubt, there's oil, there's water. There's no doubt in my mind. Whereas something like a float-based technology, I don't know. What do they do when there's no oil or water? They still got to float.
Karl, any more questions on the chat? I don't know if I would see them.
Well, unless they posted them to everyone, I'm not going to see them. All I've seen is the posts to everyone, and there aren't any questions that way. If you guys posted a chat question, go ahead and speak up now. You can unmute yourself. We'll give you a few minutes to any more questions. Go ahead, guys.
John, I got a question for you.
Okay.
Why are you showing stuff left of the zero? Why are you showing negative stuff?
When you say left, you're talking about this way?
Yeah. Why do you start at -10 there instead of 0? First of all, how do I see negative, and why would I want to?
Okay. So normally this would be the default, would be like -11 inches. This kind of shows us our spring pin connection. This is our reference pulse where that microwave travels onto the probe. There are times we'll ask you to read back maybe 60 inches. And you can do that by doing, if you go to view and just do read, we'll update this. We'll say negative 60. That's going to go back and that's going to read everything in electronics. So when we do this, we can get a signature of what this would be the electronics of the radar here and here. And then this is the spring pin connection. So we can see all this. There may be times where if you're just looking at this and you see a problem here with something, but you can't tell what's going on in the electronics. So we may ask you to actually read back, and then we can tell if all this looks okay. And we can even go back and pull a production plot with that serial number, and we can see what it looked like when it left our factory versus how it is now. So we can tell if there's moisture, something going on with electronics, maybe it got a transient hit, something like that. So that's a good way for us to troubleshoot too. Normally, if you're just looking at an echo curve, this is not stuff that really concerns you, but it does us at times. And that's when we would ask you to read back negative.
I just realized we hadn't covered that at all. That's, sometimes we need that.
Yeah. It like I say, normally not so much. Normally we're concerned reference pulse, like you mentioned, should be at 0. Threshold, amplitude, stuff like that usually falls between the 0 and the bottom of the tank. That's all we're concerned with. Anything to the right of it, we're not reading. Anything to the left of it, it really doesn't matter unless there's a problem.
So I will say this, there's times that interface peak, that P2 interface peak with the pink line in it, there's times that it will appear to be below the bottom of the tank. So it's going to be right of the red line, but the arrow is going to correct it back to inside the tank. So just because the microwave takes so long to get to it and come back, it looks like it's outside the boundary of the tank. But if that arrow is correcting back to inside the tank, it's working right, and that's a real echo.
Yeah, that's common. If you have 10 feet of oil in the tank, that interface, and you have a foot of water, that peak's going to be back here somewhere below the bottom of the tank with an arrow coming back. It does freak people out sometimes.
So that's the only time you'd worry about echoes that are happening outside the red lines, right? Is if it's an interface and it's real, it might be outside the lines.
Yeah, no, that's a good point. Yep.
Anything else? PJ, you got anything? Everybody's quiet.
So
John, you had one more thought?
I have one more comment. So I don't have an example of it right here, I don't think, but let's say you had a tank, you had level, and then your interface went down to nothing, so you lost your interface. So you only had level, your interface was reading 0. Sometimes instead of going to 0, your output for your interface will read like 6 inches. And what it's doing is reading the top of the weight. So if you put the tank height 6 inches lower, which is pretty common, we normally say put the weight ½ inch off the bottom of the tank. The weight is like 5.5 inches tall, so that's 6 inches, right? So if you put the probe length to the top of the weight, which is 6 inches above the bottom of the tank, interface goes to 0, which it should be 0, it'll actually show 6, and that's because it's reading top of the weight. You can fix that. If you have to have it show 0, then just make your probe length the same as the tank. It's the probe length is not that critical. The tank height is the one that really matters. I've seen this a lot come up.
And another solution is you can order these with the 2-inch tall weight, right? And then you can get that 6 inches down to like 2.5 inches. So if you order the short the short stubby weight that can move that down a little bit.
Yep. So we have a little bit of time left. Does anybody have any questions, or I can go back over any of this with the live device here?
David, Tyson, Sheldon?
I don't got anything now. Thanks, though.
Yeah, I think I'm good. Pretty much covered about all the things I was questioning, but
Yeah, well, when you get out in the field next time you're working on one, you'll have more questions. we do all the time.
Send them to Karl.
Hey, Karl, this is Sheldon. Can you send this recording to us, our team over here?
Yeah, absolutely.
Okay, so we ready to stop the recording and sign off?
10, 9, 8, 6, 7, 5, 4, 3, 2, 1. No more questions. We're going to call it. Guys, thanks a lot for joining us today. I hope you got something good out of this. And, like Wayne said, next time you hook up to a radar, you're going to have questions. Just give us a shout. Let us know what we can do to help.
Great. Thanks, guys.
Awesome. Thanks, everybody.
Thank
Thank
you.
you, gentlemen.
Thanks, guys.